All right, so we're just going to finish up section 5.1 notes that we didn't get to in class. What I've done is I've basically written out, so if you want to pause and then come back to it while I go over it. Also, 5.2, I found videos from like 4 years ago when I taught this class 4 or 5 years ago. So I'm going to post those videos for you to look at instead of me having to create new ones. So you could just ignore any comments if I talk about dates or deadlines in that video because that was pertaining to my old class. All right, let's get started. So lemma 5.1.4, if S is a finite set with cardinality K and X is any object not an S, then S union, the set containing X is finite and has cardinality K plus 1. So let's look at this proof. Well, suppose S is a finite set with cardinality K and X is any object not an S. So like I said, when you're supposing something is finite, then you sort of look at it in two cases. That S is equal to the empty set and when it's not. So if S is equal to the empty set, then we know the cardinality is 0, which is our K. Thus, if we add another element, S union the set containing X, that's just going to equal the set containing X, which is finite since it's equivalent to N1, right? And also the cardinality, so I use different notation for the cardinality, is 0 plus 1, which is going to be K plus 1. So usually the case where you're looking at S being or your set being equal to the empty set, that proof should not be too long. All right, well now let's suppose, well, if S is not equal to the empty set, then since we already know it's finite, it has to be equivalent to n sub k for some k belongs to the naturals. Well, since x doesn't belong in S, then we can say that the set containing X is equivalent to the set containing k plus 1, all right, which would be disjoint. So that means they would be disjoint. And so thus by theorem 5.1.2a, S union the set X is equivalent to n sub k union the set containing k plus 1, which will give us n sub k plus 1. And you should go back and look at that theorem to make sure you understand how it fits in this problem. Therefore, S union the set X is finite and has cardinality k plus 1. All right, so the next lemma that I want you to prove in your notes, I'm not going to prove it in this video, is this. For every k belongs to n, every subset of n sub k is finite. So prove in your notes, and if you don't understand anything in that proof, just bring it back. We'll go over it sometime next week. When we come back from the break. All right, so this is one of the big theorems, and then the last thing is the pigeonhole principle that I'll talk about. But here, every subset of a finite set is finite, okay? Well, let's start this proof. So assume S is finite and T is a subset of S. If T is equal to the empty set, then T is finite, right? Well, let's assume it's not equal to the empty set. That would tell us that S is not equal to the empty set, right? Because T is a subset of S. Okay. So that tells us that S is equivalent to n sub k for some k belong to the naturals, and there exists a function from S to n sub k that's 1-to-1 and onto, right? So the restriction, which you should remember, so the restriction of F onto T, right, that would be a 1-to-1 function onto the range of F restricted to T. And you can see theorem 4.3.5 that talks about the restriction part in 1-to-1. Well, if that's the case, thus T is equivalent to the range of F restricted to T, but the range of F restricted to T is a subset of n sub k, right? And your book has a very nice picture. I didn't draw it here, but your book has a very nice picture sort of setting this up. So if you want to look in the book and put that in your notes, you can. And thus the range of F restricted to T is finite by lemma 5.1.5. I think it's 5.1.5. Therefore, T is equivalent to n sub k, and thus T is finite. So hopefully that made sense. And like I said, if it doesn't, then look at that picture that's in your book. All right. Theorem 5.1.7. See that book for theorem and proofs. I think it's 3 different parts to it. So look at that. That talks about cardinality, I believe. Okay, so the pigeonhole principle to me is just one of the most straightforward principles. Not proving it, it takes a little finesse, but it's not difficult. Using it in the proof, I should say, it's not difficult. Proving it is a proof by induction, which I'm going to have you do on your own. But this is also called, it's different names for it. I think it's called the mailbox paradox. Um, but basically, it's called the pigeonhole principle because the way you want to think about it is this. Let's say you have 5 pigeons and 4 pigeonholes. And so if that's the case, if you have 5 pigeons and 4 pigeonholes, I like to think of in terms of mailboxes and letters. So if you have 5 letters and 4 mailboxes and you want to put those letters in a mailbox, then there is at least one of those mailboxes will have more than one letter, right? That just makes sense, right? Because there are 5 letters and 4 mailboxes. So at least one of those mailboxes will have 4 letters. That's what the pigeonhole principle is saying. And they talk with the pigeonholes and pigeons. I'm not for sure why they thought of pigeons and pigeonholes. So yeah. But let n, so this is saying let n and r belong to the naturals. Let f be a function from n sub n to n sub r. If n is greater than r, so if n is greater than r, then f is not 1-to-1. And we sort of talked about this indirectly in class, right? We talked about when we're looking at, well, if it's 1-to-1, if it's onto, and I think some students have made some conjectures saying that if your domain is greater than your codomain, then it cannot be 1-to-1. And that's what this pigeonhole principle is saying. See the book for the proof. It is a little involved, so if it's not clear or any steps in that proof isn't clear, then just ask me. You can email me and ask me, or you can, we'll have a chance to sort of review if you have any review questions. All right, but I wanted to do an application because I think I'm doing this. I think this is one of the problems I gave you for homework, so you're welcome if that's the case. If not, you should know how to do, you should be able to do these problems that's similar to, that's using the pigeonhole principle to prove. So it says, give a proof using the pigeonhole principle for the following. The Italian village of Solomeo near Perugia, I think that's right, has a population of 400. Prove that there are at least 2 village residents with the same birthday. And in fact, when I've taught, I've taught statistics, and so when I teach the statistics, there is a high probability, I'm not for sure the probability, but it's definitely greater than 50. I want to say it's like maybe 80% probability that says if you're in a room with at least 30 people, 29, 30 people, then there's an 80% probability that you can find 2 people that have the same birthday. And you would think, wow, that wouldn't be possible, but there is. So if you're ever in a large setting or a large group with more than 30 people, and you're doing like an icebreaker or you have time, see if you can find at least 2 people who have the same birthday. Okay. But this one is saying that they have 400 people, right? So because there are only 365 days, we're just looking at the standard number of days. We're not including a leap year or anything. But since there are 365 days and 400 people, then in fact, they're going to be more than just 2 people, right? But all we have to show is that there are at least 2 village residents with the same birthday. Okay. Well, here's the proof setup. First, let A equal the set of people in Solomeo. Let B equal the calendar days in a year. So that means the cardinality of A is 400 and the cardinality of B is 365, right? Well, then that means we should be able to, we know that A is equivalent to N sub 400 and B is equivalent to N sub 365, right? Because you see it's finite. So that means there exist bijections, F that goes from N sub 400 to A. And remember, because the equivalence is an equivalence relation, it's symmetric, and we're doing this strategically in sub 400 to A instead of A to N sub 400, and you can do that because it's symmetric, right? And G, we keeping G the same. It's going from B to N sub 365. And then we proceed with contradiction. Well, let's assume no 2 residents have the same birthday. Then that would mean if no 2 residents have the same birthday, then there would exist a 1-to-1 function from A to B, right? Let's call that H from A to B. If no 2 people have the same birthday, that's what we're saying. So if we compose, so G composed with H composed with F. Remember, we start with the inner one, so that domain is N sub 400, and then we look at the output, the codomain in G, which is N 365. So that means N sub 400 to N sub 365 is 1-to-1, since compositions of 1-to-1 functions are 1-to-1, okay? Well, however, this contradicts the pigeonhole principle since 400 is greater than 365. Thus, every function capital T, from A to B is not 1-to-1. Thus, or hence, no matter what the birthday assignments may be, that should be separated, so not together, at least 2 residents will be mapped to the same birthday. And that's it. It's really, okay. And that's it. It's really straightforward. So I'm done now with section 5.1 notes. You should be able to complete the homework that's going to be due on Tuesday. What else? I think that's it. Oh, and so I'm going to post the 5.2 videos from what I had way before. So again, just ignore any dates or deadlines on there. I think the homework problems I give, you can practice. Remember, I'm not collecting homework for 5.2. I just want you to practice some problems. And I'll see you all after the break.